important and why that award was given out. And then I was just talking to Rin, maybe we'll do something in January. We will not have one in December because it would be on December 21st. It's just too close to the holidays. We were talking about, I don't know if you've noticed that LIGO has been in the news quite a bit. Maybe we'll see if we can get somebody to come and talk about LIGO for January. If you have other suggestions, that's what those feedback forms are for. I would now like to introduce our speaker. And that's a different. So this is Russ McDonald, and he is a Deputy Director of the National High Magnetic Field Facility, Pulse Field Facility in the Materials Physics Division at Los Alamos National Laboratory. Russ joined the lab as a postdoc in 2001 after earning his doctorate in physics from the University of Oxford. You might hear an accent. Studying the optical properties of organic superconductors at high pressure, as we all do. His research specializes in high magnetic field measurements of correlated electron materials, such as high-temperature superconductors, quantum magnet systems, and materials with Dirac.
Doesn't matter. Dirac.
Correct me. How is it pronounced?
Dirac.
Dirac. Dirac and topological non-trivial band structures. A recent highlight of his career was a world-setting record of 100 Tesla non-destructive magnetic pulse in March of 2012. And it did get news around the world, or as I like to call it, the sound of science. And with that, allow me to present Russ McDonald.
Thank you very much. Okay. I've spent the day talking to third and fourth graders, hence all the cool demos and things that I was playing with school kids all day. I will try and pitch it at a very similar level. Rein me in if I go off at some tangent. Luckily, I haven't got anything to write on, draw on, or any slides to distract me with. So I thought I'd start by just saying what we do here with high magnetic fields in material science. And I think to demonstrate that, I'll start actually by showing you something that I still find incredibly neat. And that is, I've brought with me a piece of high temperature superconductor. It looks like a little black ceramic puck. It doesn't look particularly like most of the conductor we're familiar with, the copper that we have in our wiring, in our walls, in our plumbing, in our homes. And start by basically saying, we don't understand why this superconducts. There's been 30 plus years of us knowing about high temperature superconductors. We understand a lot about conventional metals and how they superconduct at very low temperatures, how it involves the sound waves in the material. But we don't understand this. And a lot of our measurements with high magnetic fields and a lot of our use of high magnetic fields is to do material science, looking at the way electrons behave in materials, the way electrons behave in materials that lead to high temperature superconducting phenomena, that might lead to exotic magnetism, that might lead to all sorts of interesting behavior. And I'll try and give a flavor of some of that today. But I thought nothing speaks volumes than seeing a superconductor levitate on a magnetic track. So this is just a load of very, very strong bar magnets. I won't put my phone or credit cards near them. And you can see copper is a non-magnetic metal, it doesn't stick. This piece of high temperature ceramic is also not magnetic. And what I'm going to do is I'm going to sit it in this little styrofoam cup that I trimmed down for the kids earlier today. And I'm going to take some liquid nitrogen and I'm going to pour it on top, and I'm going to let it get cold while I keep talking to you. And then hopefully not blind myself in the process. Styrofoam. I mustn't get this confused with the wine while I'm doing it now. So here we go. I'm going to sit it there, and those of you that are close can see that it's sort of boiling furiously. So liquid nitrogen, liquid air. 80% of what we're breathing is nitrogen. If you cool it down to about 75 degrees above absolute zero, up here, up a mountain, the pressure's a little bit lower, so the temperature's lower, it will liquefy. And it's sat there and it's basically boiling because it's got this rather hot piece of ceramic superconductor in there. Okay, so let me back up a little bit while that's cooling, because that can take some time. we tend to understand the difference between, say, a metal and an insulator by the way it behaves. One fundamental difference might be that at first order, a metal conducts electricity, an insulator doesn't. A slightly more refined description might be that the conductivity of a metal gets better when you get it cold. The conductivity of an insulator gets worse when it gets cold. We tend to understand these differences in terms of what we call the band theory of metals. We think about the dispersion relation, the relationship between the energy and the momentum, how hard it is to accelerate the electrons in a material. And we think about how many electrons with filled shells, filled bands, and we think about it very much like, if I take my wine glass here, if I think about the wine sloshing in the glass, I don't really care, and we can be an optimist or a pessimist, if the glass is half full or half empty. What I care about is that there's some empty and some full, and I can really describe the sloshing by the motion of the liquid that's at the surface. I don't care what's happening down here, I don't care what's happening up here. If I had a completely empty glass, there's no possibility for sloshing. If I had a completely full glass and did this, there's no possibility for sloshing. That's very much how we understand conventional metals in terms of have the electrons got somewhere to move. The way they move through a material is very much modified by the environment they're in. There are many times Avogadro's number of mobile electrons in this copper, and yet they all kind of see each other. They're charged. There's Coulomb interaction between them, Coulomb interaction with the iron cores. There's sound waves. All this is going on. And yet for copper, the electrons behave very much like an electron in free space would. Its mass looks rather similar, or the ability to accelerate it by an electric field or a magnetic field looks rather similar. A lot of interesting materials, whether they're semiconductors, whether they're interesting magnetic materials, whether they're high temperature superconductors, have a rather unusual relationship between the energy and the momentum. So they're either harder or easier to accelerate. And in fact, that's not just because of an interaction between them and them seeing all the atoms that they're rattling past, but in fact, all the other interactions, and that's a lot of what we do in high magnetic fields, is trying to understand these many body effects, these interactions between the other electrons and the sound waves give rise to interesting properties. At a very hand-waving level, that's what gives rise to superconductivity, and certainly low-temperature superconductivity is electrons seeing each other and seeing an attractive interaction rather than repulsive, because they both have a positive charge, because of a sound wave that they're exchanging. High-temperature superconductors, there's a lot of evidence that basically says their motion is governed because of the interactions. So it's like my ability to walk across the bar here tonight. If it's pretty empty, I can do it just by avoiding the chairs and walking across the bar. If this is a crowded bar and it's heaving, I have to interact with all, and there's some sort of correlated motion across the bar. So it's like me moving through a soup rather than moving as an individual. And what we do with high magnetic fields is we try and understand that motion of electrons. So it's like we have a microscope on the motion of electrons. So before I go on to that, let me see if this has got cold enough, and maybe we can see. So I'm going to spill some liquid nitrogen, and hopefully my superconductor will stay behind, and it's going to float backwards and forwards on here. So I always find that quite amazing. To I can take a piece of paper and pass it underneath, and it's basically bouncing backwards and forwards. That's basically, and there you can see as it warms up. Oh, hopefully it didn't break. It lost its superconductivity. And went back to being a rather boring piece of ceramic again. So, in my mind, that's a very visual and surprising demonstration of a correlated state of matter, meaning the electrons in there are no longer behaving as individuals.